Hey, how are you doing, guys? I'm Dohan. Here's lesson 5.1, which is about style transfer using Fastai. So let's get started. These are objectives for today's lesson. So after completing this video, you will know what exactly is a style transfer and how to implement it using Fastai Library. And I'll also give you an introduction about Nbdev, how to use it, and we will go through it in more details in the next video. And lastly, I will show you how to create your custom loss function. Okay, so here's our outline, so let's get started with our lesson. Okay, so before we get started, if you're doing this in Collab, you need to ensure that you have P100 GPU. So by using this line of code here, you can check that you work with P100 GPU. As you can see here, we have P100. And if this doesn't work with you, you can force Collab to give you a better GPU by making a 1000 by 1000 by 1000 tensor as we made here. And now let's go with a light introduction to what Nbdev actually is. So Nbdev is a library for creating Python packages directly from Jupyter Notebooks. It was developed by Fastai team to make it easier to create and maintain open source software projects, especially in the field of deep learning. So with Nbdev, you can write your code and documentation in Jupyter Notebooks and then use library's command line tools to automatically generate Python modules, unit tests, and documentation from those notebooks. So this allows you to iterate quickly on your code and documentation and to keep everything in one place. Okay, so let's go with a few sort of terminologies. So we have default export, hide, and export. So for the default export is a special command that specifies a default module that a notebook's code should be exported to. And the hide command tells Nbdev to exclude the cell that's added to from the exported module. And the export command tells Nbdev to include the cell that's added to in the exported module. So as you can see here in the code, we use hide command because we want to exclude the cell containing comment from the documentation generated by Nbdev. And for the second line, we import all functions and objects defined in Shodek module of Nbdev. So the Shodek module provides tools for generating documentation from notebooks, including functions for displaying documentation in a Jupyter notebook or as HTML. And here we import our vision library from FastAI. And now let's go with the interesting part of the video, which is style transfer. So what is a style transfer? It's a process of using neural network to take the style from one image and apply to a completely different image. So we call the first image the style image, and we call the second image, or the one that we are going to apply the style to, the content image. So if we see here, we have our content image and we have our style image. So if we apply our style transfer on both, we have this output image that combines the style from our style image and the content from our content image. So style transfer utilizes something called feature loss, and this is used to describe the difference between the features of the content image and the generated image. So if we go back, the feature loss is going to calculate the difference between our content image, this, and our generated image, which is our output image. So as I told you, the goal of style transfer is to generate a new image that combines the content of one image with the style of another image. To achieve this, a common approach is to use a pre-trained convolutional neural network such as VGG to extract features from the content and style images, and then the feature loss is calculated as a difference between the feature maps of generated image and the content image. So the idea is to minimize this difference. And we will see more when we start building our feature loss. Okay, so let's go with our pre-trained network. So we are going to use VGG19, which is a small CNN pre-trained on ImageNet that has only 19 layers. So here we set it up to you to use either VGG19 or VGG16. And since we are not training, so this is just the evaluation. So here we want to get a pre-trained model, gather its information, and then turn it to a coda, because we are going to run everything on GPU and set it to evaluation mode. So this means that we don't keep track of the gradients and our weights never change. And then we want to be able to get the internal activation features from our model. So in order to do that, we will get rid of the head. So here we make sure that in our feature net, everything that requires any sort of gradients is set to false. And here we define layers list that used to extract specific layers from the pre-trained VGG19 model, which can be used for feature extraction. And here's what each part of code does. So first we have feature net, which is a pre-trained VGG19 model loaded in FastAI as we saw. And this list here is a list of indices of layers that we want to extract from the model. And the overall, so this is a list comprehension that iterates over the list of indices and select the corresponding layers from VGG19 model. And the selected layers are then stored into a new list, which is our layers here. And here's a configuration for VGG16 and VGG19 models. And now we are going to summarize all of what we have worked on into quick functions. So part of this is going to be for deployment code, and part of this allows us to get rid of any extra code in case we want to work on style transfer. And since the function has an underscore, so this is a private feature, so our users cannot directly access them. So here we create our getFeatures function that takes in a string for our architecture and make sure it's pre-trained. And then go ahead and grab the hooks from our models layer. So if you don't know what are the hooks, they basically gather the weights at particular layers so that we want the hooked activations, and we are going to train this sort of feature comparison model based on these hooks. So as you can see here, we call our getFeatures function, pass it our VGG19, and store the result into fetch variable. So for our loss function, as I told you, we need an image, which is the content image, and the style image along with activations from our encoder. So we will use this image as our style image, and also you can go ahead and play with another style image. So let's grab our style image. This is the URL for that image. And here we download an image from the specified URL and save it as a style.jpg in the current directory. So we can now make a pipeline to convert our image into a tensor to use in our loss function. So we will want to use the datasets for this. So here we define our dataset, pass it our style image, and we say that we want PIL image.create. And then we make our data loaders where after item is just to tensor. And for after batch, we convert it from int to float tensor. And then we make some sort of normalization. And here we define our batch size to be equal to 1. And here we show our input image with our transformations applied to. And as you can see here, we grab the raw value for our image and store it into a style image variable here. And here we print its shape. And then we make a quick function that goes ahead and grab any style image from any URL you pass. And here we grab the features from our image using fits functions that we made earlier. And for now, let's take a look at their shapes. So here we loop for each feature from the extracted features and print its shape. So as you can see, here is the result. And now we can bring those images down to the channel size. So as you can see here, we define the gram function that's used to compute the gram matrix for a given tensor. So the gram matrix is a way of measuring the correlation between different channels of a convolutional neural network feature map. Okay, so let's go with how the gram function works. So the input to the function is x, which is a tensor of shape n, c, h, and w, where n is the batch size, c the number of channels, h the height, and w is the width of the feature map. And the first line of the function extracts the values of n, c, h, and w from the shape of x. The second line reshapes x by flattening the spatial dimensions of the feature map. And the third line computes the gram matrix of x by multiplying x by its transpose along the channel dimension 1 and dividing by the total number of elements in this feature map, and then the gram matrix is returned as the output of that function. Okay, so as you can see here, we compute the gram matrix for each feature map in our image features list. And here we print their shapes. And then we define another function that takes a list of feature maps as an input, and it will return a new list that excludes the last feature map in the original list. Let's look at why that was important. So we have something called style loss and something called activation loss. So in a style loss function here we have input features and output features, and we are going to calculate the mean squared error for all of the stylized features by comparing how they look compared to our original image. Okay, and here we are going to our feature loss. So the important bit that I want you guys to take away, even if you don't understand quite the concept, is how we can make these custom loss functions and how FastAI expects them. So here we are going to make our loss function. So the first thing is each time we pass an image, we don't want to update the encoder's weights. So we are not going to keep track of any of the matrices. So this what self.reset matrices does. And for forward is exactly like our models forward. So first we get the features of our predictions and target, and then we calculate the style and activation loss, and then store the loss and return the sum. Okay, so for reset matrices is going to initialize a dictionary called matrices with two empty lists, style and content. So this method is called to reset the matrices before starting a new training epoch. And add loss here takes style and activation losses as input and append them to the corresponding lists in the matrices dictionary. Okay, and for activation loss, it just does a mean squared error of the activation layers themselves. Then we make an instance of our loss function. And now we can build our architecture. So we are going to create a variety of layers for us to use. The first thing we want is a reflection layer. Okay, so let's go with our reflection layer. So the first thing we have is the dunder init dunder method, which is initializes the module by defining the necessary layers. So the first layer we have is a reflection path, which is a PyTorch layer that pads the input tensor with a reflection padding. And then we have this conv2d, which is a PyTorch convolutional layer that performs a 2D convolutional operation on the padded tensor. And then we have the forward method, which defines how the input tensor is passed through the layers. So the input tensor x is first padded with the reflection padding and then passed through the convolutional layer. Then we are going to make our residual block. So here we are defining two reflection layer instances, each followed by an instance normalization layer and ReLU activation function. And for the forward method here defines how the input tensor is passed through the layers as I told you. So the input tensor x here is first stored as a residual and then x is passed through the first reflection layer instance followed by an instance normalization and ReLU activation, and the resulting tensor is then passed through the second reflection layer followed by another instance normalization, and finally the output of the second reflection layer instance is added to the residual and the resulting tensor is returned. Okay, and then we have upsample convolutional layer, which is another reflection layer, but we have also some upsampling done in the very beginning. Okay, and now let's go and declare another model, and as you can see here in the code, it's not cleanest, but we can understand what each of them are doing. So in the beginning, we declare our transformer net, and first we have this series of reflection layers that start at 3 and go up to 128, and then we have some residual blocks, upsampling a bit more, and finally we have this reflection layer. And if we look at our forward method here, it's very explicit in showing what it does, so you can go through it. Okay, and here we make an instance of our transformer net. And now let's define our data loaders. So we will be using Coco sample dataset. Okay, so first we grab our data by using enter_data method. And then we are going to define our data block. So our data block is going to pass in an image block and pass out an image block. And for transformers, we have only resize and normalize. And here we define our data loaders, pass it our dataset and a batch size of 22. And here we show a batch of our data. Okay, and now we can make our learner. So here we pass it our data loaders, our architecture, and our custom loss function. And as you can see here, we call learn.summary method. And here is the total number of parameters and the total number of trainable parameters and so on. Okay, so let's find a learning rate and fit for one epoch by using lr.find method. So we will be using a learning rate with 10 to the power -3. Okay, and here we fit for one cycle. And now let's take a look at the results. So as you can see here, we started with an image of little girl. And now we have something similar to our style image. Then we save our model. And now let's try learn.predict. So here we have a cat image and we will try learn.predict on it. And now we show the result. And as you can see, it doesn't have the best quality. So why we have that? Because when you do predict, it will run the same training transforms. So let's fix that. Here we load our model. So first we are going to create a dataset similar to how we did for the stylized image. And then what we can do is actually grab one batch, and the first instance in that batch will be our image. And lastly, we can run it to the model. And now let's try that again. So if we go through and show our image, it's better than before. So that's it for today's video. Hope you enjoyed.